Lab 2, projectile motion workshop. The fundamental principles used in this lab 2 were about Newton's second law and how the acceleration of the object or the momentum of an object over time gives the net force of the object. The position update and velocity update formula was also used in this lab. The position update, which is initial position, is equal to average velocity over time, and the final velocity is initial velocity plus acceleration times time, as well as how the net force was equal to the force due to gravity on the object, and as well as the drag force. The purpose of this particular lab is to study projectile motion using observed data in the tracker and real-world experiments, and as well as computational modeling from the script. And this lab studies projectile motion using these ideas for the The main idea of the lab was studying the motion of projectile objects, which results in a constant velocity x, assuming no drag, while velocity in the y changes with an acceleration due to gravity, assuming no drag. However, it's discovered that since drag applies, these conditions do not always apply, and the velocity is actually quite different. The procedure was record the motion of a waterjet paper using tracker and reduce it to a collaboration point, and analyze how it changes, how the x and y position changes over time, as well as use computation modeling to compare it with the real world example. The setup with the system and the surroundings, where the system was the one that picked the ball, and the surroundings was everything interacts with it, like the air, gravity, etc. And as well as these initial conditions were assumed, where gravity and the force due to drag are the only two forces acting on it, and these initial conditions from the tracker model were used for the computational model to create the computational model. Part one of the experiment was projectile motion and using a tracker, and the table to the left shows the time versus the x distance and the y distance, as well as the graphs of this data. There are some sources of error in this example, such as incorrect measurements and calibration mistake, incorrect calculations for the point mass, axis being incorrect, etc. Part two was tracker, where only gravity was used initially, and key equations were used in this closed loop model, such as what F net is equal to the force of gravity plus the force due to drag, the position of formula and the block vector formula. And these graphs further show the position versus time graphs created by both the code as well as the table. Part two of the lab was gravity and drag being considered now, where the equations are the same, but the force due to drag can no longer be zero, as shown in the previous slide. The force due to drag is now a non-zero value based on the value of b, which is the drag constant in this specific situation. And this graphs also shows the updated position time graphs with drag now being considered. Results. Clearly, all three models shown to the right, the real-world example, gravity only using gravity plus drag in the computational model, are similar, and they show the same turning point, and they show object and projectile motions. However, there are instances. It's clear that the object that simulates only gravity travels farther, as drag does not oppose it. When drag is considered, the computational model gets closer to the real-world example, but there are still differences, which can be due to the other confounding variables like the surface area of the paper, if the paper was tossed in the z-axis, etc. What if the object was thrown straight up? So with the same initial speed, time to hit the ground would actually be longer, and this is due to the fact that there'd be a larger y velocity since the projectile's speed is no longer split into the x and y components, and all this speed, initial speed, is only the y, and therefore the velocity in the y would be larger when it's thrown straight up, and it would take longer to hit the ground. And what does it mean? The no drag model, no terminal velocity as speed increases linearly with time on the way down due to the constant acceleration. The drag model, it can predict terminal velocity, but the cost is too short, so a terminal velocity is still not reached. But if you want to measure terminal velocity, you would do a vertical drop from a very high stairwell. And in the last few seconds, when the velocity in the y is flat line, we can assume terminal velocity has been reached since there is no net force, and the force of drag equals the force of gravity. Thank you.